right, so welcome everyone. This is Astronomy 101, Week 2. We are going to be talking about discovering the universe yourself. And this is just going to be part 1. Because there's a lot of stuff here that is conceptually pretty difficult to wrap our heads around. And even I have to kind of take a step back and go, okay, what are we talking about? Oh, thank you, Betty. I'm glad. I'm really happy to be here too. Even though I was kind of frantically putting some of this together. But it's more of just the sense that, like, first of all, I'm not constrained by a semester. So it's not like I'm being told you have X amount of classes to get through all of this material, which is kind of nice. And we'll hang out here. Oh, Aaron's okay. Thanks, Domestic. No worries. Some people call me Dr. Aaron, but Aaron's fine with me. Thank you for asking. But because we're not constrained of like, oh, the semester's ending on this day, so we have to blitz through some of this stuff and hope you catch up. This in particular is one where I feel like we lose a lot of people when we learn astronomy, because it's conceptually trying to figure out what the night sky looks like to us and how to talk about the night sky when, especially in Astronomy 101, when we are limited to like our star system and our planets and everything like that. So I just want to kick things off by talking a little bit about what we did last week, which is the idea that, you know, our cosmological address, that we live on a planet in a star system, which is one star system out of billions of billions of stars in our galaxy. See, this is how it happens. The Milky Way galaxy is our home one. And then we are part of a local group of galaxies out there. And then that local group is part of a supercluster, and then the rest is our universe. So if we were going to write an address, it would be Earth in the solar system, in the Milky Way galaxy, in the local group, in our local supercluster, in the universe. Now, it's all... I'm sure if you talk to aliens on another world and you said, oh yeah, I live in a local group, and they're like, that's what my local group is called, that would fall down really fast. But for our purposes, it works fine. And the big kind of takeaway that we really tried to drill home last week is that space is very big. And even light, which travels super fast, takes time to travel through our universe and get to us. So when we're looking at things in space, we are seeing them as they were when they sent that light, because that light took time to reach us. Also, a light year is a unit of distance. It's the amount of time, or it's the distance that light travels over the course of 1 year. And parsec is also a unit of distance. We didn't get into the parsec definition. We will start to scrape away at that this week. And hopefully it will start to make sense, because like I said, the parsec definition is pretty hard to wrap our brain around. And exactly phrase, one of the best lines ever. How vastly, hugely, mind-bogglingly big it is. Before we get into this week's lesson, I wanted to talk about what is in the sky this week to look out for, particularly because I'm not going to assign homework, but there's going to be a lot in here that you may want to go and try out for yourself. So, tonight is a new moon. So that means that the moon is between us and the sun. Now, it's not an eclipse. It's slightly either above or below, but it's not perfectly in line. That only happens occasionally. Again, something that we'll get to, and we'll learn about how those alignments all work. But it just means that there's no reflection. So we are not getting any light reflected from the moon. That's what's called a new moon, and that's happening this week. And the reason that that's important to point out is because it means that especially this weekend, it's going to be very, very good for observing dimmer objects. So if you do have a telescope or you're starting to practice astronomy, this weekend is a good weekend to try to find dark objects. On Tuesday, and I have to thank Andy for bringing this to my attention. On Tuesday, there is a comet currently traveling through our solar system. It's called Comet Swan. It is, if you're in the northern hemisphere, it is very low on the horizon. But Tuesday is going to be its brightest point, and I think it's going to be about, this is going to make sense by the end of this lesson, it's going to be about 20 degrees above the horizon, kind of around sunset, and then within like an hour or two, it's going to be kind of near the horizon. So it's going to be a little bit hard to see, but if you are able to see it, look out for Comet Swan. So those are kind of the two things going on this week. Not a ton of like cool planet stuff. I think Titan you can still observe if you have a telescope, one of Saturn's moons. And Pluto, I think, is also in a good visible position, but only if you have a telescope. So, kicking off this lesson, we are talking about discovering the universe for yourself. So we are going to be discussing what our celestial sphere is, what constellations actually are, and how we talk about the size and the distances between objects in our night sky. Like I said, if you are coming in a little bit late, that's okay. But we are going to be taking this part a little bit slower than we normally would in Astronomy 101, because this is hard to kind of, it seems superficially pretty easy, but then once you kind of start trying to picture all of it, it takes a bit of brain warping. So try to stick with me. I will record this. I will post this, so you can always go back and check it out. But for us, if we go outside and we look up at the night sky, we can see, if you're in like no light pollution, dark area, no clouds, you can see about 2,000 stars plus the Milky Way, which in this case, we're defining the Milky Way as the band of light across the night sky. What our mind does is when we look at all of these stars, we organize them into patterns. And we call those constellations. Now, pause, because I can feel the responses of being like, all right, I just wanted to learn some astronomy. I know what a constellation is. Well, do you? And because I forget this every time. And then when I go back to teach astronomy, I'm like, oh yeah, that's what a constellation is. So a constellation is not the picture that you get out of making a pattern out of stars. It is a defined region of the sky that those patterns help us find. Over, centuries and centuries of cultures from different parts of the world, they all view those patterns differently and fit that into their culture and their mythology. And so, but there still has to be some standardization for this. And I'm glad. See, at least if you heard it, it might be like me, you just forget it, which is what I do. So there are 88 official constellations being these patterns that are mapped out. So I did find this somewhere. So thank you. So you can use these patterns in the night sky, and these are the ones sort of, Western culture has identified them as. You can use those to find those regions, but when astronomers are talking about like, oh, it's in the area of Orion, that could be the area up here, the area down here, over here. It doesn't necessarily have to be within the Orion constellation. And you can think of it kind of like states almost, that if we talk about breaking up states, we do have well-defined borders, even though it's not like you cross over from, like Colorado to Wyoming, and as soon as you hit that border, everything changes. This is just, we have to define these lines, and we create these defined regions. And so the International Astronomical Union in 1928 actually laid these out and defined what those constellations are and what the mapping out of all of those is. So we're familiar with constellations. And a good kind of trick, actually, I'll bring this up again, but if you do have some software or like an app or something, the sort of code, like guidance, I guess, guidelines, not actual rules, guidelines that astronomers use is that if you can teach yourself and learn to identify 20 constellations in the night sky, you're pretty good. Like, you're going to feel pretty comfortable looking up at the night sky in your local sky, which we'll talk about, and feeling like you understand that. So if you want some homework, try to, over the course of the next few weeks, try to learn 20 constellations and take your time, but there's lots of great apps out there, and I can discuss some of those as we go. So the celestial sphere, we're going to define, and I'm actually just going to blitz through this, and we'll go through it one at a time. But the celestial sphere is that idea that when we look up at the night sky, it looks like it's all on a dome around us. That we don't see the perspective, like we're showing here, of the fact that these stars are not necessarily close to each other in space. They're just projected to us like they're on a sphere, like being in a planetarium, right? So it's all about the perspective that we're at. Using this celestial sphere, even though that this was around in the beginning of ancient astronomy, the idea of the celestial sphere was literally that we were at the center and the night sky was a hard sphere that was rotating around us. That's not the case, but it does help us to use what we call the celestial sphere to identify things in the night sky. Now, there are 4 key components of the celestial sphere that we use when we're talking about what's up in the night sky. We have the North Celestial Pole. Now, this is take Earth's North Pole and go straight up. So projected right up from Earth's North Pole. That's the North Celestial Pole. Straight down is the South Celestial Pole. So we're not worried about the tilt of the Earth yet when we're talking about the North or the South Celestial Pole. We're just saying it's above, just think of Earth. What's above the North Pole? What's above the South Pole? We also have the Celestial Equator, which is where you take the North Pole and you take the South Pole, and we have the equator, which bifurcates the Earth, and you just project that out. So along the celestial equator, straight up is north, straight down is south, and then we have the celestial equator that is just, if you took our equator and sent it out, that's where that marks. But the Earth is tilted. And this just annoyingly breaks everything. Because it would be really nice if Earth just sat like this, where the North Celestial Pole is up here, the North Pole is like this, and it rotates, and its equator is flat, and then it orbited the sun just like that. Then we'd be hunky-dory. Unfortunately, the Earth is tilted about 23.5 degrees. And so that means that our equator goes like this, and the ecliptic comes in at a different angle. So that's what we're marking out here. The ecliptic is basically the path of the sun. So as the Earth goes around, and we will drill this into your brain, if it gets to the point that it's annoying, that's a good thing. Because this is all stuff that, again, superficially, you're like, yeah, I know the Earth is at an angle. Yeah, I know we go around the sun. Yeah, I know that's the cause of the seasons. But when we're talking about trying to figure out where things are and the orientation and all of that, you do have to kind of pause and be like, okay, especially when we're thinking about like Earth looking out versus looking down on Earth. All of this right now is going to be Earth looking out. We're thinking about this celestial sphere. And as over the course of the year, the sun traces out this pattern because the Earth is moving around at an angle. It's annoying as all get out, but it is what it is, and that's what we have to deal with. So, and you can see the constellations here marked out as well. But the important thing to take away here is the 4 points of the celestial sphere is the North Celestial Pole, the South Celestial Pole, the Celestial Equator. All of those are Earth-centric. Then the ecliptic is thinking about the sun and where the sun appears to be throughout the year as our stupidly tilted Earth goes around the sun. Again, we'll come back to it plenty of times. So the Milky Way in the night sky, I mentioned, we're talking about the Milky Way in the sense that we're talking about the streak of light in the sky. Again, Earth-centric, local sky. It's the band of light in the night sky that circles all around the celestial sphere. So I'm actually going to go back And you can see it kind of marked out here, that they have marked out this Milky Way, and it does trace all around and do that. So it's this band of light that you can see throughout the night sky. It is actually the brightest. It's brighter in the southern hemisphere. It's easier to see. I can confirm that. Of course, when I was in the southern hemisphere, I was in the middle of nowhere, so it's a little bit biased there, but it is really pretty. And the Milky Way in the night sky traces out the galactic plane as it appears from our location in the Milky Way galaxy. This is stupid terminology that covers two things. When we talk about the Milky Way, we are talking about our own galaxy, but we're also talking about it as an object within the night sky. But when we're thinking about that celestial sphere, right, we had the North Pole, the South Pole, the equator, celestial equator. We had the ecliptic, which if you trace out the position of the sun throughout the year, you will build out this ecliptic plane, because that's the plane that we live in our solar system. What's kind of cool is when you're looking at the Milky Way, again, this is something that we know, or maybe you're learning for the first time, but as it sinks in, the cool thing about this is that we are looking down the plane of our own galaxy. So when we talk about all of these, equator, the ecliptic, and then we have this galactic plane where we are showing essentially our position and our rotation as we're moving through the Milky Way galaxy, which is pretty baller, if I do say so myself. The dark spots in the Milky Way are not the absence of things. They are darker, denser clouds that are obscuring stars that are behind them. So it's actually making it harder to see kind of through our Milky Way. And here's a way that we can kind of think about it. So again, artist rendition of the Milky Way galaxy. And I sort of vaguely, we're about 2/3-ish out from the center-ish. What I'm showing here is, think about this being a very, very not to scale image of our Earth, right? And we're talking about our celestial plane. When we're looking out, we can look down this ecliptic. And we could talk a little bit more about kind of throughout the year, it changes kind of just with Earth's like rotation and everything. But it's important to note that, our lifetimes are not necessarily moving around here. This is just our tiny, 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 tiny dot in the Milky Way galaxy. But when we're looking at the Milky Way at night, we are looking down the plane of our own galaxy, which is awesome. And if you look to the constellation of Sagittarius, you will be looking directly toward the center of our Milky Way galaxy, which is awesome. Awesome. Okay, so our local sky. I'm going to pause for water. Our local sky is basically taking the celestial sphere and going, well, okay, we're talking about from the perspective of the Earth what it looks like, but from my perspective, I'm only going to see half of that celestial sphere because ground. And that's a limiter to what we're able to see for us just going outside and looking up. Now, like I said, we define the local sky as seen from wherever you are standing. So this is your local sky, and it's a hemisphere or a dome that's because you're only seeing half of the celestial sphere. And this is where it starts to get hooey really fast, because you then, you can project your position on the Earth and then draw out a celestial sphere and then think about, okay, the Earth rotating on there. It can be a little mind-bendy, but we'll drill it home. It's pretty much exactly half, because we could kind of nitpick it a little bit that the Earth is round, and so for a certain point it's going to be dipping down a little bit, but it's effectively half, because we're able to look around in all directions. Now, obviously, depending on where you live, your horizon might be at a higher elevation for things like for things like mountains. I grew up in Colorado, and so the mountains are going to add an increase to the western horizon, so it's going to be blocking out that area. But in theory, you would just be left half. And yeah, perception breaks everything. So the key references that we use when talking about your local sky, these are important definitions. We have the horizon, right? That is this boundary between the Earth and the sky. Zenith, if we say something is at zenith, that is directly overhead. So it's a 90-degree altitude, which I'll define altitude next, but it's directly above you. Your local sky zenith is directly above you. The meridian is if you point north and then you trace up above your zenith and then down to the south point. That traces out the meridian. Meridian half-ish. Try to think about it that way. It's basically just a line that you say. And so we use the terms zenith and meridian all the time when we're talking about references to where things are in the night sky. Like, oh yeah, it's just a little bit east of the meridian. Or it's, a little bit south of zenith, and all of those things. So it's really important to think about when we're talking about the night sky. Now, how you actually find stuff and how we talk about the location of objects in the local sky, this isn't too bad, but stick with me. You basically start facing north, and then you'll get a direction that we'll go to in a second, which is called the azimuth. So what you do is you start north, and then you go clockwise, and azimuth will be given to you in degrees. So you basically say, okay, 360 degrees makes up a circle, so I'm going to go around this circle, and then when I'm directly east, that's 90 degrees. When I'm directly south, that's 180, and then 270, and then back to 360. Remember geometry? So if we have north, you go about 90 degrees, and then you continue going on clockwise. Now, they didn't mark out what the azimuth is here on this diagram. What they marked out was the altitude. So when you're finding something, you move from north clockwise till you hit those degrees, and then you stay there, and then you do you trace out the altitude again, like degrees. You start at 0, you go up directly above is 90, that's your zenith, and then you keep going, and your maximum is going to be 180 because you only have half of a sphere that you're looking at. So this one in particular, we're given that it's 60 degrees altitude. Also, sometimes this is called elevation. So if you've heard that, or you have an app that will say, oh, it's, 78 degrees elevation, that's the same thing as azimuth. Or altitude. Jeez, sorry. Altitude. So you go from north. This is, you hit 90. So we can say this is maybe 135. It's halfway. Say it's 135 azimuth and 60 degrees altitude, or 60 degrees elevation. So you go whoop, and then you go whoop. That's how that works. Now, talking about angular sizes and distances, we're using degrees for this. Again, 360 degrees makes up a circle. That's important to remember. And the thing to keep in mind, I am glad that you're here watching it live and then recording it so you can go back. But definitely take some time to think about this. And I'm even going to take some time to walk us through some examples live. And we can spill into the Q&A with that. So if you want to see something or you want me to do something, let me know. Anyway, it's important to remember that when we're talking about the local sky and the celestial sphere, we're always talking about our perspective. Becca pointed that out. It's all about perspective and perception. We have no depth perception on our celestial sphere. We just imagine that it's all mapped out at one thing. So we can't actually judge the actual size or how far apart everything is. All we can do is talk about their angular sizes and distances because we're using a sphere as an example. So we can describe these angular sizes or separation as it appears to you. So the angular size is the angle that it appears to span. So if we're looking at something, I'll show a picture, but if you're looking at something in the sky, you're saying, okay, it's about that much. Imagine it's a whole circle. That's going to be like a degree. And then angular distance is the angle that the angular distance that two objects seem to be apart. So you have one star here, you have one star here, and you say, okay, they are 20 degrees apart. That's the angular distance. You're not worried about how far they actually are from each other in space. You're just worried about how far apart they are from your perspective. And because it's projected onto a sphere, we use angles. And this is an important, and it makes sense from this. The example that I'm using is that the moon appears to be about half a degree. And the sun, if, you had a filter and everything and actually were just able to see without looking directly at it, the sun, it's about half a degree as well. But the moon is much smaller than the sun, but the sun is very far away. So very small, far away. Any Father Ted fans will like that joke. Cool thing is something you can play with as you're kind of thinking about this and trying to distill this, is our hands are actually great for this, and astronomers do this all the time. There's a whole host of ways you can measure degrees. The easiest one is your finger is about 1 degree. So if you look up at something, if your finger covers it, sort of head it out that way, that's about 1 degree. Your fist is 10 degrees, spread out fingers are about 20, and then 3 degrees, 4 degrees, and 6 degrees. It's just nerdy and fun. And again, angular distance is that angle between them. Yeah. And the angular size is how big an object is measured in degrees. But this one, stick with me. We will be coming back to these units. This is like a primer for this. I will go over this as many times as people want me to. A degree isn't necessarily going to cut it because there's a lot of stuff in the night sky and there's a lot of things that are very small or very close together. So a degree is not going to be enough. So we break down degrees into arc minutes. So that 1 degree is going to take 60 arc minutes, and then that arc minute is going to be broken down into 60 arc seconds. So tiny. I can't even show you on here as an example. But because, this is what astronomers use. Because we have telescopes, because we're able to look out at the night sky, you will be looking at things that are arc seconds apart, fractions of degrees. So this is not to scale. This is not 1 degree of a 360 degree circle. It's just zoomed in. But you take 1 degree, you break it apart, you have 60 arc minutes. We use 1 dash for an arc minute. And then 1 arc minute is going to have 60 arc seconds within that. So just like a clock, you think about it like a clock if you want, that you have, 60 minutes in an hour, and then each minute has 60 seconds. That's essentially exactly what it's coming from. And you can see this is how we write out the location of objects. We say it's 24 degrees, 37 arc minutes, and 10 arc seconds. That's how you would say that. So how we find things in the night sky. Now, we're at the half hour, but this is why we take our time. We're slowly going through it. Recall azimuth and altitude. Azimuth, point north, go around a certain amount, and go up to your altitude. And then you can use, to be more specific, arc minutes, and even smaller are arc seconds. So I'm going to pull up my favorite software, which is Stellarium, which is free. You can check it out for yourself. And this is right now at Griffith Observatory, because I didn't want to put my home address in here, but it's close enough. And the legendary farmland of Griffith Observatory. It's not, it's in the middle of LA, but you get the idea. This is right now, so we're going to get rid of the atmosphere. This is what it would look like if there was no sun. But I want to point out some objects here. So we can look at Sirius, and it pulls up all this information. And if you're able to get close to your computer, or you can record this later or pull it up yourself, they have a ton of reference points for this. But we've learned here we have as and alt. That's azimuth and altitude. And it's 144 degrees, 37 arc minutes, and then lots of seconds. And it's moving because the Earth is rotating. And this is measured by your local sky. So because the Earth is rotating, and this is looking east, so it's going back this way, it's slowly moving through the sky because the Earth is rotating, and it is measuring your local sky is azimuth and altitude. Now you have these ones up here that aren't moving. We will learn about those. These are like fixed reference points that we use because when you're trying to talk to an astronomer, you're running a telescope and the person who needs the data are at different points on the Earth, and you're like, yeah, it's at this azimuth and this altitude, that's going to mean nothing for them because they're in a different location in the night sky. But you can see that azimuth and altitude change throughout the day. And if we continue along, you can kind of see the Milky Way here. Do I want to talk about that? I will talk about this briefly. This is called Stellarium, and you can download it for... They have a multitude of things you can play with it. It's pretty cool. You can have red sky, like night mode, so you can take it out at night with your laptop, and it won't ruin your night vision, which is pretty sweet. So that is azimuth and altitude. You can look at these different objects in the night sky. They all have a different azimuth and a different altitude. And that's important. So we're going to look at Polaris, the North Star. The North Star. And you can see that its azimuth, first of all, it's not moving very much. And its altitude is at 34 degrees. Now, I'll come back to this here. Yeah, stars rising and setting. We are going to come back to this. I said this is part 1 of doing this. But Polaris is the North Star. So this up here, looking at Polaris, you are looking towards that celestial North Pole, right? We talked about that. Now, it's not moving very much because these objects move through the sky due to Earth's rotation. And if you think about it like, think about just the celestial sphere. Don't think about the angle or anything like that. You have the celestial sphere, Earth is rotating, so all of those stars from sitting here are that celestial sphere is going to appear to rotate. And we can play with that. So let's speed up time. Boom! So you can see the night sky rotating around the celestial North Pole. Now this is obviously the northern hemisphere. If you have the southern hemisphere, which I can go to if people don't have questions or anything, we can jump to that. But you can see those are all satellites flying around because this contains satellites as well. But you can watch it rotating, and it's rotating around the celestial North Pole. I will touch on all these later, but I want to lay the groundwork now. We call these stars circumpolar stars, the ones up here, because they never set throughout the night. As night turns into day and turns into night again, these stars are just going to go around the celestial North Pole. Another cool fact with this is that if we do actually think about Earth's tilt, that this is pointing toward Polaris, and it's tilted about 23.5 degrees. So you can actually, please don't get hung up on this. This is a teaser for next week, but you can start thinking about it. This is where it starts to break your brain. But Polaris is at 34 degrees north. LA is at 34 degrees north. So it's so up to our North Pole is the same degrees as your latitude on Earth. And we will go back into that next week. We will talk about kind of how our celestial pole tilts, and then you measure the latitude from that. But if I said that and you were just like, oh yeah, that makes sense. Great. Good on you. So yeah, it is pretty cool, Beckett. I agree. All right. So that is it for part 1 of this hot nonsense that will give you a headache. And I get it. I've been there. I've been in your shoes. It hurts. It takes time to think about. I would say the best thing for this is to just honestly get outside and look up and just start trying to find some constellations. There is so much awesome free stuff out there that you can look for. You can look to try to find objects. My favorite one that I have, obviously Stellarium is my favorite on the laptop, but I use Skyview on... Oh, I better not do that, actually, because it's got a camera on it. But Skyview is a free app on your phone And what it does is you literally, like, it's got, you know, its gyroscope, it measures your location, and then it maps what's on the sky behind you. So you can turn, if you want to play with this, if you can't go outside, if you don't have anywhere outside you can go that's safe and away from people, you can open up Stellaris or open up Skyview or any number of things, and then you can turn off all the labels and start looking for constellations yourself and see if you can identify them. And you'd be amazed at how actually you do start to find things, which is pretty cool. All right, our first question. Andy asked, what's my favorite constellation and why? Mine is Orion because it's easy to find. And I'm not that, I talk a big talk, but I'm not that great at night sky astronomy. I don't like calling it amateur astronomy because the amateur astronomers I know are a heck of a lot better at finding planets and stuff in the night sky than I am. But mine is Orion because it's easy to find and because it's got a lot of cool stuff in it. First of all, it's got Betelgeuse, and which is objectively awesome. And it also has the Orion Nebula, which is actually, if you have a really good telescope, even just yourself, you can actually take a really cool picture of the Orion Nebula. So I'm glad you're not good at it either. But that's my favorite constellation. So question is, how different are the galactic and the ecliptic plane? They are considerably different. Let me see if I have a good picture of the galactic plane compared to, I mean, I guess the best one I have is we can just go back to this, all right, that's probably an easier way to do this. This one, because this is tracing out, so if you're here on Earth, right, up near the North Celestial Pole, that's where you start to see the Milky Way. And then it does track all the way down and back up again. So they are very offset from each other. So very funny. Should be Cancer. Whatever. Aquarius here. But nice try. And yeah, agreed. The amateur is a misunderstood word. It means love of, which I like a lot. Yeah, M42. That's an object within Orion. And yeah, Brad mentioned Skyview let him formally track a European satellite last week. That's one of the cool things we can do with it, is you can actually find objects in the night sky. You can search for satellites and the International Space Station and everything like that, which is pretty sweet. If people are typing questions, I will just keep showing us cool stuff. Let me see if it pops up here. Is this maybe? This stuff is crazy. But if we want to talk about the galactic plane, you can kind of see the galactic plane here, which is awesome. Awesome. And then if we go down to let's go down to like Australia. Now let's go to Darwin. All right. So in Darwin, you can see here it's really sharp. That's the galactic plane going up like that. And it's the middle of the day there right now. But if we let it set, and so we used Polaris in the northern hemisphere. In the southern hemisphere, they have the Southern Cross, which is really easy to find, but actually doesn't necessarily point. It's not at the pole. You have to watch it for a couple hours. So you can see this is the Southern Cross here. And what it's doing is it is making it points toward the South Celestial Pole. So at any point you can find south by just drawing a line through the cross and it's pointing south. But in order to actually find the south celestial pole, you have to let it draw. There's the sun. But yeah, and you can see the galactic plane here moving as well. That's awesome. Okay, do we have any other questions? Is there anything you'd like me to... I have no problem. I've got 20 minutes booked for this, so if you want me to go back and, like, do this again, we can go through the local night sky again, and azimuth and elevation and celestial plane and all of that as well. I'm more than happy to do that. But if you just have any random astronomy questions, that's okay too. I will hang out as long as we like. Yeah, so comets. So yeah, at the top I mentioned the Swan comet is going to be visible in the night sky. I doubt it's in here because it was only recently discovered. Let's go back home. My home. And this is now a couple days from here. But there is a meteor shower. The Aquarids meteor shower is happening. And no, don't need that. Swan, yeah, they don't have the Swan comet in here yet. But the Swan comet is going to be there, and then there's also the Atlas comet, which I think is visible right now, but I think it's getting dimmer, as it was. And the Swan comet is more visible from the southern hemisphere, and it was only recently discovered by the Swan telescope. That's what they named it after. But pretty cool. So let's then, while we're here, while we have this open, let's talk about. Oh, that's a great question. Yeah, so when we talk about our galactic plane, that Milky Way, where we are looking down our own galaxy's plane. And that's literally the path, like that's where we would rotate in. Galaxies fall into two categories. One is called an elliptical galaxy, and one is called a spiral galaxy. Spiral galaxies are more flat. Elliptical basically means other. And we still, because the tricky thing with astronomy is that we can't watch stuff happen in real time because it is so difficult to, because it takes so long for things to happen. But we can sort of put puzzle pieces together. We can say, okay, as we look back in time, as we see older galaxies, the galaxies that we're seeing way in the distant past that are only a few, maybe 100,000 million, 100 million years-ish after the Big Bang, there are more elliptical, non-flat, globular type galaxies out there. As we look more closely in our neighborhood, which is recent times, there are a lot more spiral galaxies, and those are the flat ones. So you can run simulations with this, and essentially what you can do is you can take two globs of particles and have it just be 1 billion particles in each glob. Set physics, set gravity to go. You could even have them be all the same mass, right? You just are saying, I have a whole region of particles that have a certain mass here, whole region of particles with a certain mass here. Gravity's the only thing here. And you hit go. And they start to come towards each other. Now, because space is very, very big, stars are very small relative to the sort of galaxies that they're in, you're hardly going to have any collisions. Hi, Emily! Thanks for hanging out! So you're hardly going to have any collisions happen as they start to pass through each other. And then, if you let it keep going, they'll kind of pass through, but they'll be trapped in the gravity. And they'll pass back, and they'll pass back. And eventually, angular momentum will take over, and they will start to do this. And because you have angular momentum, it flattens out. And you end up with a flat spiral. It's pretty cool to watch. It's one of the things that, like, as an undergrad astronomy student, usually like your late junior, senior year, you have to code that. And it's pretty cool to watch. If little Emily has a question, we can talk about it if we want to ask about favorite planets. And yeah, exactly. Only 100 million. I mean, it's scales of space, man. That was our first week. That's like, you do have to get used to thinking it's only 100 million. That's nothing in space terms. Existential crisis 101. But, so I hope that answered your question. Again, we can't actually see galaxies merge. We can't actually see them flatten out. But the theory is that over time you have these clusters of stars that are a type of galaxy, that if they merge, they start to flatten out. And so our galaxy is a flat, big spiral galaxy. We do have galactic neighbors that aren't spirals, but they're smaller. So the idea is that they haven't actually merged with anything. They have kind of stayed these clusters of stars. So while we're here, if people are still thinking of questions or anything, let's go through our celestial sphere one more time. Because I think a couple people were saying, I'm glad this is recorded, I'm coming back to this. Which is good. So we're going to look north. All right, and let's actually highlight an object here. Pollux. So we start north. Pollux is at 80 degrees azimuth. So we would turn about, not quite to east, because east is 90 degrees. But we would turn about 80 degrees. And then it's about 40 degrees altitude. So we look 40 degrees up. Remember, 90 is directly above you. So about 40 degrees up. Then we would find Pollux. So that's how the azimuth and altitudes work. We have zenith, which is directly above us. So, that's the Subaru cluster, I think. So that's pretty high. And it starts to break the program once I start to look directly up. But zenith is directly up. Meridian is the line that you trace out by going north all the way through the zenith and into the south. And the horizon is this horizon. We can get rid of it here and just say, all right, here's our celestial sphere. Here's everything. We're treating it all as a big globe that's around us. There's our galactic plane. I don't know if I can make the ecliptic show on here, but it would essentially trace out where the sun goes throughout the year. Let me see if there's any other previews I can come up with to help preface next week, because it's not going to be too bad, but it's a little bit mind-bendy. But yeah. Any space questions are welcome while I have a look at what we're doing next time. So yeah, our variation with latitude. Let's talk about that a little bit. When we talk about our latitude, we're talking about how many degrees north or south we are from our equator. So if you say, all right, I'm, 30 degrees north, 37 degrees north, I think I am. That's up from the equator. But because, oh geez, yeah, I don't think I'm ready to talk about this. I do have to prep for these sometimes because it's so hard to explain these. We can talk about the seasons though. Seasons I can definitely talk about right now because we talked about how the Earth is tilted, right? And because I know we've got some kiddos watching, and that makes it easier too as well. But if we talk about seasons, let's go back to our tilted Earth, which I think I have here. Yes. So the Earth is tilted, and as it's going around the sun, let's say the sun is here, the Earth is here, and this is the North Pole. This would be winter for Earth right now. As it goes around, then it'll hit summer. And it's because of the direction that the North Pole is facing. When it's facing here, as it goes throughout the day, more of the northern half of the planet is facing the sun. And then when it's over here, less of it is. So your days are going to be much, much shorter. When they are like this and this, where the pole isn't facing one way or the other, when it's actually just aligned up, so it's not tilted towards or away, those are our equinox, that you basically have equal parts day and night, no matter where you are on the Earth. Equal night, equinox. And it is not because we are closer or further away from the sun. And that's okay if you think that. But that's not, if you had that in your mind, that's okay. But that's not why we have seasons. It's because the Earth is tilted and it's close to or far away from the sun. We were talking about comets a little bit. I don't know, Andy, if you want me to talk a little bit more about them. But the comets are different from asteroids. This is something that we'll get to again later as well. But comets come from a part of our solar system called the Oort cloud. So we have our planets. We have our sun. We have 8 planets. We have our asteroid belt. And we have the Kuiper belt. And beyond the Kuiper belt, we get... we have something called the Oort cloud, which is a lot of these objects, and it actually makes a sphere around us as opposed to living in one plane. So sometimes we get objects from the Oort cloud that come in and orbit the sun and then go back out, and they come in at different angles. So domestic, Tropic of Cancer and Capricorn. Those are, yes, those are the latitudes, which are 23.5 degrees north and 23.5 degrees south. So when we're talking about, this is really hard without visuals. I promise I'll have pictures for this stuff next week because it is good to see. When we are talking about the sun throughout the course of the year, you will always have a point if you are above the Tropic of Cancer or below Capricorn, or vice versa. If you're outside of that region, so you have the equator, 23 degrees north, 23 degrees south, those are those regions. Essentially what that means is at some point during the year, the sun will be directly overhead. For the rest of us, the sun will always be slightly south or it will always be slightly north. And it just has to do with that tilt because the sun will move throughout that ecliptic. Remember, yeah, we looked at it right here. The sun will move through this throughout the year. So you can kind of say that here, this is when the sun is 23.5 degrees north, and this is when it's 23.5 degrees south in the sky. So the zenith will be at 23.5 degrees, and that corresponds to the latitude of those lines. And again, it's because as the Earth goes around throughout the year, you build out this ecliptic region. If you project, like what we can do is, again, I'm sorry I don't have a picture for this, but I wasn't planning on getting to this point yet. But I know you're all kind, forgiving people, so so that's good. But if you can picture the sun sort of pointing directly down at different points throughout here, there's going to be, here it's really far north. It's at its northernmost point. Here it's at its southernmost point. So this would be like the summer solstice here. This would be the winter solstice down here. And yeah, I hope that answered your question. The whole latitude corresponding to the sun thing, as you can see, it's a mind trip. It's hard to get our minds around. But it's really trying to think about our motion throughout the solar system. So even if it never clicks, which is totally fine, even if it never clicks, don't worry. Like there's still plenty that you'll learn a ton. You'll learn a ton. If it never clicks, that's okay. But if it does help start to understand what's going on throughout the year and throughout the Earth's motion around the sun, it's pretty cool. That's the cool part of astronomy. Another neat thing that you can do that we used to do, if you want some homework, I can always give homework. But so trying to learn 20 constellations, that's a good thing. That's like you will have reached sort of peak astronomy at that point. But another fun project you can do is over the course of like a month or two, go outside at sunrise or sunset, but make sure it's the same thing every day. So make sure you can commit to it because sunrise is getting earlier. But if you go to the same spot, whether it's if you can see the sunset from your house or sunrise, wherever you can find a spot, go to every morning, or at least every other morning, and draw your horizon bring that drawing with you every morning and mark where the sun is throughout the rising, because you'll see the sunrise change throughout the year, which is pretty cool to see. So that's kind of a fun project to do. So on that note, I will end it here. That's okay. I appreciate all your questions. I know this is, I get it. I get it. I know this is a little bit hard to wrap our heads around. We will come back to this. I will have a much better explanation of the latitudes to the North Pole, the elevations and everything, next week. The software I showed you was Stellarium, which is free. And they also have Skyview, which is a phone app that I use. I recommend both of them to try to learn stuff. Try orienting yourself in the night sky is always fun and a good project to do. And then next week we'll continue plowing away from this. And feel free to send me your questions. I'm obviously always happy to answer them, figure it out, go back, come up with a good answer. But we are going to be talking next week now about the seasons, how the night sky changes throughout the year. So exactly all the stuff that we touched on a little bit here. How Earth's axis changes over time. And we'll maybe touch on the moon if we can get there. But, oh, thank you, Bene. I know, I hope I didn't give anyone too much of a headache, but it's Friday, so. All right, well, thank you all for hanging out with me. I really appreciate this. If you are watching this recorded after the fact, please, well, even if you're here live, please hit follow. You can subscribe here on Twitch for $4.99 a month, or using your Amazon Prime membership for a free subscription. If you're on YouTube, you can like and subscribe, which helps me get views and continue doing this, because I really enjoy teaching astronomy, and I don't mind teaching it for free because I think it's fun. I think I love doing it. I think there's a lot of really smart, cool people, all of you out there who want to learn this stuff, and so I'm happy to bring it to you. You can check out my links down below under the About section for my Twitter, my website, my Patreon, my donations page, and all those things. And thank you. I will be back on Sunday at 11 Pacific to do our Star Trek brunch. And then I will be streaming on Monday, just playing around with games. And then we will be doing our episode club the following week. And I do know what they are, but I don't have them off the top of my head. So I will post that to my Twitter when we get there. And Becca, I will answer what a variable star is next week. So that will be the first question of the Q&A section. So thank you guys very much again. I really appreciate it. I appreciate you sticking with me. I love you. Take care of yourselves. Thank you. It means a lot. All right. Until next time. Live long and prosper.